to, so far we've talked about passive walker and then once per step control where we chose, for example, the foot placement to be at a certain angle, and we really didn't care about how the foot got there and so on. But when you're actually controlling robots, very important to control the foot all the way from where it is right now to where it's going to be in 0.5 seconds or 1 second or whatever. So this part is about trajectory generation, which basically is very important when you're actually doing implementation on hardware. Trajectory generation. Okay, so what's going on here is we have, if you think of a graph of position versus time, there's an initial position. Okay, there's the initial position and there's a final position. And there is a time at which we have these two positions. We want to join these two with some trajectory. And then there are many options, right? You could do this way. You could go that way. Clearly, it's very zigzag and not recommended. Or you can just draw a straight line. That does not look like a straight line. Hold on. Straight line. Okay, so how do we connect 2 points? Well, we could draw a straight line like the one shown in green. And the question is how, well, this is just showing the line graphically, but really we need to feed the motor or the actuator with some command Q as a function of time, right? And so if you want to think of 2 points joined by a straight line, then we can think of an equation of a straight line, which is A0 plus A1t, right? So it is a first order equation. Okay, so the question is, how do we find these A0 and A1, which are constant? Let's just call this Q0. Let's call this point QF. Let's see, QF, yeah, Q0 and QF. And so what we do is to find these constants, A0 and A1, we pretty much substitute these values. So we put Q0 equals A0 plus A1. Let's call this T0 and T0. And then QF equals A0 plus A1 TF. And so we have two equations, two unknowns. And then we can solve for those unknowns. So if you solve for those unknowns, you get A0, A1 equals 1 divided by TF minus T0. And then what you get in the numerator is Q0 TF minus QF T0 divided by QF minus Q0. Okay, so that's the formula. I didn't do it. Let's know. This is basically a 2x1 matrix. So I did not do this by hand. I actually used MATLAB to do it. The symbolic toolbox will do this for you. So if you put these values inside the formula for Q, you get something like this. Q of T equals Q0 TF minus QF T0 divided by TF minus T0. That's for the constant part. And then for the non-constant, the A1, we have QF minus Q0 divided by TF minus T0 times T. Okay, so that's the formula. If you now try to find the velocity, which is the rate of change of position, then the first term will clearly be 0 because it's all constant. Q0s and T's are all constant. So we get QF minus Q0 divided by TF minus T0, which is, by the way, a constant, right? Which is not surprising that we got a constant for the velocity. So now if you do a plot, so here's a plot of Q versus T. You'll see that that's basically a straight line. And then if you draw a plot of Q dot versus T, then you should see something like this. This is T0 TF, T0 tf, t0, tf. And so you'll see essentially a line like this. Okay, so what does that mean? Well, if you look at the way this starts, at time t equals 0, it's at 0 speed. And then in no time, it has to speed up to a constant speed and then maintain that speed and then slow down instantaneously to 0 speed. And so this is an unnecessary transient, which is not good for motors, right? So we want to avoid having these transients. So how do we solve this? So we want to avoid this. Well, we can avoid this by setting up more conditions. So what we can do is we can go for a cubic polynomial. What a cubic polynomial will do is, well, first of all, let's define the things we want. First of all, we want q0 at t. So at t equals t0, we want q equals q0. That's the initial position. We still want t equals tf, q equals qf. Okay, those are the two conditions we had earlier, but we also want to ensure two more conditions, which is we want to set at t equals t0, 0 for q dot, and then at t equals tf, we also want the velocity to be 0. So it starts at the right position with 0 velocity, ends at the correct position with 0 velocity. So we have 4 conditions, which means we need a cubic profile. Okay, so what does that look like? Well, it will be q of t equals a0 plus a1t plus a2t square plus a3t cube, right? And then we have 4 conditions and 4 equations. And so we can solve for those 4 equations and solve for q. And if you do those q, so once you do that and you solve for those unknowns, you can plot q as a function of time. You can plot q dot as a function of time. So q as a function of time will no longer look like a straight line, but in fact, it looks something like this. Okay, it starts at that position you want, ends at the position you want, but then it's more curved around the edges. And that's because you can see the velocity here is 0. So initially the velocity is 0. The final velocity is going to be 0 because of this curvature here. And then some point it's going to hit a max velocity. So the curve will look like this. Okay, so we have avoided this transients for the velocity. However, if you draw a plot of q double dot versus t, okay, then you'll see that at 0, the acceleration is non-zero. Somewhere it becomes 0 midway, and then it goes negative. So it goes something like this. So what's going on is this, that initially at time t equals 0, we see that the acceleration is 0. It suddenly bumps off to some value. Then it decelerates, goes negative, and then goes back down to 0. So then this is a problem. This is a transient. And that can damage motors because now we have essentially an acceleration, a certain acceleration from 0 to some value. So, well, how do you avoid this? Well, you can avoid this by saying that you enforce 2 more conditions. You already had 4 conditions, positions and velocity, but you can have 2 more conditions. And those conditions are that the acceleration at the start and at the end should be 0. And that will give you together 6 conditions, which means you need a 5th order polynomial, and then you can solve that and get the profile. And then if you do that, you'll see that your position, velocity, and acceleration will all look smooth, no transients, but your third derivative, which is called jerk, is going to have a transient. So you want to avoid that, then you need to keep increasing the polynomial order. And so that is something which keeps going, and you just don't want to keep increasing, ramping up the order. So what you eventually end up doing is you stick to some order. Let's typically fifth is good enough, and then you don't go to seventh and ninth, and then you just live with fifth. Okay. Now you can use this idea to do more than just going from point A to point B. What if you wanted to go from point A to point B via some other point? So I'll do a short example on how to do this. Okay, so extend this idea to via points. What are via points? So sometimes you want to go from point A to point B. This is the start. This is the goal. And then you want to visit some intermediate point. Right? So you go here, you go to this point, and then you go there. Okay, so for example, if you want to swing your leg, that is, you want to ensure that at the intermediate point, you have enough ground clearance. So that point would then be something which avoids your scuffing of your legs with the ground. Okay, so that's just one example. But for a manipulator, it could be you want to go to some point and pick something up, and then pick something else up before you will end up at the goal position. And so what you can do in this case is basically, given the problem, you can then start putting these equations together. So I'll just do one example. Here's an example. Okay, so the problem is, okay, find Q as a function of time such that Q of t equals 0 is 0. Q of at t equals 1 second, it is 0.5. Okay, and then we have Q of t equals 2. It's at 2 seconds, you want to be at 1. Okay, and that 0.51 is in 1 unit. So you can see that this is an intermediate point or via point. Okay, so that's just 3 conditions, but you could have additional condition. For example, Q dot at t equals 0 is 0. So it starts off with 0 speed, and it should also end at 0 speed. So the end is 2 seconds, should be 0. Okay, and then the question is, what happens at the via point? Now, what happens at the via point is up to you. You could specify that the via point velocity should be 0, or you could specify some value. So in this case, so at via point, let's assume Q dot of t is 0.2. Okay, so 0.2 is the velocity in some unit, but it could be 0, it could be 5, whatever. Most of the time, you don't specify a speed, you just set it to 0, and then it just proceeds to this. Now, let's look at this problem closely. I've given a bunch of conditions. I told you to find two trajectories. Well, I told you to find one trajectory, but really, instead of doing one trajectory, you want to break it into 2 trajectories. So first half, since there are, I believe, 4 conditions, position, velocity, I can choose one profile, the first profile, to be cubic profile. So A10 plus A11t plus A12t square plus A13t cube. Okay, so that will be from 0 to 1, and then from 1 to 3, we would have A20 plus A21t plus A22t square plus A23t cube. So we'll have that will be from 1 to 2. Okay, so now we have 4 and 4, 8 unknowns, but we do have 8 equations. So let's see what those equations are. So first of all, q1 of t at 0 is going to be 0. Then we have q at t equals q1 at t1 equals 1 is equal to 0.5. So that's the second condition. Then we have q dot at t equals 0 is 0. Okay, so that's this one. Okay, then we keep going. Then we have q1, sorry, my bad, q1 at t equals q1 dot at t equals 1 is also given, it's 0.2. So I write that down. Then q2 at t equals 1 is 0.5. q2 at t equals 2 equals 1. q2 dot at t equals 1 is 0.2, which is given here. And then finally, at the end, we have t equals 2 is 0. So we have 8 equations. So we have 8 equations, 8 unknowns, and it's kind of very straightforward to solve for the 8 equations from 8 unknowns. So it boils down to writing a linear equation and then solving it. So let me just show you the code before we go to the next part. Okay, I'm going to share you a bunch of different files. Okay, and well, I did a lot of programming here to do different trajectories. So for example, if you want to do cubic, this is one of the first examples I showed. Here I actually have an analytical formula, I copy pasted it. If you run this, okay, this is basically showing the cubic polynomial. So you have the q and q dot, which I showed you. I basically jotted down on paper, and then you have this acceleration, which is non smooth. So then if you go to the next one, which is let's see, so I only have linear and cubic, so I don't have the fifth order, but you can easily do that. So this is the example one which I just showed you. So essentially there were 8 conditions and there were 8 equations. I put them in an A matrix, the left hand side of the equations. And by the way, these equations are all linear, so you can use inverse to solve for them, or you could do A/B. So here is, I'm going to show you the plots which I get for those for that problem which I just wrote on paper. So the blue line shows, the blue solid line shows the position for q1 and velocity and acceleration for q1, and then the dashed line shows the position, velocity and acceleration for q2. Okay, so you can see that the position is continuous. The velocity here is also continuous. So the velocity here is 0.2, exactly at midway at t equals 1. And then if you look at the acceleration, the problem with the acceleration is that at 0, you would suddenly get an acceleration of 2.5, and then it decreases, and then it suddenly decreases from, increases from minus 2.2 to 0, which is basically introduces this bad things onto a motor. And then you get the same thing with the second profile. You see the acceleration is actually discontinuous. So if you want to avoid this, you want to put more conditions which will make that equation be fifth order, right? Now there's another problem with this kind of profile. The issue is that the acceleration here is, the velocity here is sort of, it's 0, but then it blows to 0.7 before it goes down to 0.2. And the problem is many of these motors have a limit on, the motor controller have a limit on how much velocity you can make these things go. You don't want them to hit a maximum, hit a max like this. You want to rather go up to a max speed. Let's say 0.4 was the max speed. Maintain that max speed and then go down to wherever you want to go. So in other words, most of these manipulators or robots are so configured or so controlled that they try to achieve a maximum speed without having these huge transients. So you want to avoid them. Now it turns out that you could write your own code to generate that kind of motion, but I found that the Robotics Toolbox actually has these commands which you can use. So I'm going to show you 2 of them from the Robotics Toolbox. One of them is called polytraj, and the other one is called trap-well-traj. Okay, let's just run this first. Okay, so what's going on here? Well, in this case, I define a number of points. Okay, so the good thing is that you can generalize it to number of points. I define a cubic trajectory. Okay, so this is actually is an extension of the cubic profile I showed you. I showed you cubic profile for one or two sections, and I had to do a lot of math. Here, they actually do it by themselves using code which MATLAB has written. So you just call cubic polytraj, and it'll take care of everything. It'll basically give you q dot, q double dot acceleration, and if you want, so that's a cubic. If you want to use the fifth order, you can also do that using a quintic polytraj. Okay, so if you, in this case, I've set it to first use cubic polytraj. So if you look over here, it's basically tracing these points 1, 5, 6, 3, and so on. So you will have starts off at 1, and then it goes to, I think, 5, 6. It's difficult to move this. Okay, that's 6. Supposed to be at 2. It's very close to 2. And then at 3, it is 6. So it's 6 at 2, and then 3 at 4. So right here is 3. It's close to 3. 3.94. It's about 4.2. It's really hard to see this. Let me run this again. Okay, hopefully okay, let's see what happens at 4. So at 4.2, we have 3.94. Go up. This is really hard to do this, but anyway, so this is basically doing these points. Okay, now let's look at the velocity. The velocity, you can see that between 0 and, so it goes from 0 all the way to 1.5, and then the velocity is 0, and then it goes, should be 0 somewhere else here. So it's basically trying to hit zeros at a bunch of points. Okay, I believe you can control those using the commands here. 2 points. Okay, okay, I have to look at the documentation, but I'm not very clear of how, if you can control this, but we can just maybe search for what this command does.
You said velocity is going to 0 between transitions?
I did not set them. It was chosen by the software. So I don't know how it was chosen. So these are velocities, which, for example, starts at 0, and then this 0 here. Oh, I see the thing now. Okay. Okay, so my bad. So here we have 8 seconds. And so really what it's doing is when you give 8 seconds, it basically divides the bins of 1, 5, 6. So 1, 2, 3, 4, 5. So there are 5 bins. So it's not really equispaced. So I think if to make it easier, we should just divide this to 6 or something.
Elmo refers to that type of motion as blending if you want it to transition without going to 0 between points.
Right. So there is no blending going on here. That's what I'm trying to say. There's no blending here. So if you look at this, the other one which I'm going to show is it doesn't go to 0, I think. I kind of blanking on that, but let's see this. So here I did it much easier now because 6, and there are 6 things. So if you look here, it will actually hit 0 at every second. And this should be 5. Yeah, so now it's right. So here it's 0, and then it should be 0 here somewhere, and then 0 there, and so on. So it basically hits 0 at every single time, which is clearly not what you want. You probably want to specify a non-zero speed. So this is what you get with cubic. If you use quintic, which is 5th order, then you get slightly smoother, but still hits 0. So the issue with these profiles is that, with this polynomial profiles, is that you hit these max 10, and then here you have a max here, you have a max here, and most of these motors or controllers for these actuators are capped to go at a max speed. So instead of specifying So you want to ensure that you go at the max speed as long as you can and never really hit these high peaks. And so the command which helps you do that is actually called trap well trach. Okay, so I'm going to change this back to 5. That's easier. And now you will see that it actually uses constant velocity profiles. So here it changed. What changed was the velocity is capped. It's capped here. You can see the acceleration is no longer, it actually is constant. So the acceleration is 0 here. Well, sorry, my bad, not 0. It's constant, sorry. It's constant. And so it basically caps off the velocity. It doesn't let the peaks to come. So you can specify trajectories this way, in which case they will not basically hit zeros. So they will not hit peaks. They will be capped off. However, they still hit zeros at 1, 2, 3, 4, and so on. So MATLAB does not, as far as I know, does not have, the robotics toolbox does not have a utility where you can specify intermediate points or via points with non-zero speed. Or maybe it can be done. I've not really seen or I've not really explored this command with enough details. So ideally, you want to not go at zero speeds. You don't want to stop every time you hit a via point. You want to go at smooth speeds. And I'm sure there are more advanced libraries which can do that. One of them is called the Reflexes library. And I think Coppelia Sim uses it. So if you want a better library, it's called Reflexes library. And luckily it's free. It's been